quantum field theory and string theory. And he's become quite famous in recent years through the ADS-CFT correspondence, and where he used integrability and beta ansatz to obtain non-perturbative results in quantum field theory. Today he's going to talk about random matrices in quantum field theory.
Thank you very much. It's a great honor for me to speak here, especially since I'm not a mathematician, I'm a physicist. But of course, mathematics is the language of physics. And I'm looking forward to this meeting to learn from you many new things. So what we'll be talking about today is the use of random matrices in quantum field theory. Well, random matrix theory has a lot of uses that go from quantum gravity and numerical topology to finance. In physics, they were introduced in the 50s and 60s by Wigner and Dyson, who were interested in the spectrum of complicated quantum systems. So usually, when we're talking about quantum mechanics, we want to solve a Schrödinger equation. So we have some Hamiltonian, which is normally a second-order differential operator that we want to diagonalize. So we want to find eigenfunctions and eigenvalues that determine the behavior of the system at hand. So if we have, say, 1 degree of freedom, in the worst case, we can put the system on a computer and it will find the eigenvalues for you, but imagine that we have, I don't know, 100 degrees of freedom. So for complex systems, this direct approach of solving the Schrödinger equation oftentimes is not feasible. And random matrix theory was proposed exactly in this case to understand the behavior of complex quantum mechanical systems. So where complexity is replaced by randomness. So randomness is, well, if you don't know much about maybe complicated system, may look random to us. And so to model such a system, one may just consider the Hamiltonian to be, in some sense, random. So the immediate question that one would like to address is, suppose that we know the statistical distribution of the Hamiltonian as an operator. So what would be the statistical distribution of the energy levels? So this question, as I said, was posed first by Wigner and by Dyson. So here is a physical review paper by Dyson. So the motivation came from nuclear physics. I can quote from this paper that the statistical theory will not predict the detailed sequence of levels in any one nucleus, but it will describe the general appearance and the degree of irregularity of the level structure that is expected to occur in any nucleus which is too complicated to be understood in detail. So this was a motivation, and so here comes the model for that. So instead of considering random operators, one can consider just big matrices. So take a matrix n by n, and then send n to infinity at the end of the calculation. And so this is the simplest matrix model that one can write, where we consider so all matrix elements of the matrix have the same distribution. In the simplest case, it's just Gaussian, independent Gaussian variables. So let me write this once again. So suppose that H is an n by n permission matrix. So Hamiltonian is a permission operator. Replace it by a big matrix, and we consider the matrix elements which are complex numbers, so we take them to be independent Gaussian random variables. So the probability distribution of a particular realization would be then exponential in the square of this trace of square of this matrix. And we are supposed to take the limit of this when the size of this matrix goes to infinity after calculating statistical averages. So typically we want to answer the question about the eigenvalues. And so the problem of going from distribution of matrices to distribution of eigenvalues was solved by Wigner. And it relies on the following observation that if we consider a statistical integral over all matrices, we can, well, by change of variables go to the integral over their eigenvalues, where there will be a Jacobian factor that is the square of the Vandermonde determinant of matrix eigenvalues. And so there is some constant which is not really important for us. And then we want to take the limit when the size of the matrix goes to infinity. And now you can see that n appears here as a coefficient in the exponent. So the exponent is really, really very big when n goes to infinity. And so this integral can be calculated by the saddle point. So the saddle point equations are, well, so they're written here. They have a mechanical analogy. So if you think of ENs as positions of some particles on a line, this would be an equilibrium condition for these particles if they're subject to a harmonic Poirot harmonic potential. So this creates a restoring force that stands on the right hand side. And then there is a two-body repulsive force between any two eigenvalues. And so the balance of these two forces determines some equilibrium distribution. In fact, this equation can be solved exactly. The solution is given by zeros of, I think, linear polynomials. When we are interested in the limit where the number of eigenvalues is very big, the answer is even simpler. We can introduce the average level density so that, well, literally the number of eigenvalues in some small interval is given by the length of this interval times this density. And so then this equation can be written as a singular integral equation, linear single integral equation of the density, which can be solved. And this is the solution that was found by Wigner, which is given by the square root formula. And if you draw it in the right variables, it is just a semicircle. So this is a semicircle distribution. So this is the answer. If you are given a random Gaussian matrix, its eigenvalues will be distributed according to this semicircular law. So notice that this distribution has an endpoint. So the probability to find an eigenvalue larger than some number mu that is related to the variance of the original matrix elements is vanishingly small. So roughly speaking, mu is the largest eigenvalue you would typically find in a random matrix. So this is a very old result, and well, it's not that complicated. What I'll be talking about today is the use of this result in the context of quantum field theory, and in particular relationship between field theory and string theory. So motivation here comes from understanding non-perturbative, strongly coupled behavior of Yang-Mills fields. So Young-Mills field can be, or gauge field can be viewed as a random matrix, but also it's random field, so it is defined at any point in space and time. And the probability distribution is given by the formula where the statistical weight is defined by this by the Young-Mills section. So this finding the correlation functions of Young-Mills field is an interesting problem. It's worth $1 million. It's one of the Clay-Nathaniel problems. So you can imagine that it's really very difficult and it's hardly formidable to solve it with the available methods. But in some related systems, obtaining even partial results here are very difficult. But in certain cases where we have extra symmetries in the problem, it turns out that we can gain some glimpse of non-perturbative behavior using matrix models. So this is what I'll be talking about. Normally, well, the best one can do is do expansion in some small parameter. This problem has a coupling constant G. So if this coupling is small, we can just Taylor expand in it. And this Taylor expansion, so physicists invented a graphical representation for it. It's called Feynman diagrammatic technique. So each of these pictures actually corresponds to some analytic expression that's a multiple integral. However, calculation-wise, the integrals that appear here become more and more complicated. There are more and more diagrams. And so computing first few orders is possible, but pushing this to very high orders is not really a simple problem either. It is desirable to have some method that would avoid assuming that the coupling constant is small and obtaining the results at any coupling. And one of ideas that was put forward by Hooft in 1974 is to use the expansion in the inverse powers of the number of colors, which is the rank of the gauge group of the Young-Mills theory. So that can be also formulated in terms of diagrams. But then diagrams in the limit of large number of colors, they have an additional two-dimensional structure. So if one considers a diagram with sufficiently big number of elements, it looks as a two-dimensional surface, discretized. And so the idea, the original observation of Hooft was that if we somehow assume that this discrete surface can be approximated or replaced by a continuous surface, that gives a direct relationship to string theory, because then what we get is a two-dimensional surface in space-time, and a string, a one-dimensional object, would produce such a surface when evolving in time. So there is one spatial direction, and when we look at this as a process, then string, well, has a two-dimensional world way. But this was sort of a rough idea that was just based on similarity between Feynman diagrams and discretized random surfaces. However, there is a concrete realization of this idea, which is actually conjectural, and this was put forward by Moldasena 18 years ago, which asserts an exact relationship between field theory and string theory that lives in space with actually with 6 extra dimensions. So the space where strings are allowed to propagate has a boundary. So in the simplest realization, this space is the anti-de Sitter space with this metric. So you see that there is in addition to 4 space and time coordinates of our world, there is an extra coordinate that's sometimes called holographic coordinate. And the metric has a double pole when this holographic coordinate is equal to 0. So the space naturally has a boundary. And the claim is that the dynamics of strings in this 5-dimensional space is projected on the boundary, similarly to how holographic, how we get a holographic image from a 2-dimensional picture. So whereas the dynamics of the boundary is described by gauge fields, and in the bulk they're described by strings, but these are 2 equivalent descriptions of one and the same physics. So the statement is that, more precisely formulated, is that Young-Mills theory that has an additional symmetry, namely supersymmetry, is exactly equivalent to string theory on the product of anti-de Sitter space and the 5-dimensional sphere. So this statement can be formulated rather precisely, although it's still a conjecture, it's not proven. And the parameters on the 2 sides are identified in such a way that the coupling constant of the Young-Mills theory is maps to the tension of the string. So tension is the energy per unit length. So if tension is very large, of course the bending of the string costs energy. So if this energy is very big, then the string will behave as a rigid rod. So of course this is and in particular it will not be able to fluctuate. So this is a sort of a physical argument why the limit where tension is very big is simple. So in that limit, quantum fluctuations of the string are not important, and it can be described by essentially classical dynamics, which we understand pretty well. So as you see, on the other side of the duality, this maps to the case where the coupling constant is very big, so which is infinitely complicated from the point of view of the dynamics of gauge fields. So this relationship is a duality. It maps a simple regime on one side to the complicated regime on the other. But in between, both descriptions are equally complicated. So, well, there is a dictionary that maps quantities on one side of this duality to quantities on the other side. For instance, if you want to compute a correlation function in gauge theory, this would correspond to a string diagram in this 5-dimensional anti-de Sitter space. So one should, well, there is a mathematical prescription behind this picture. So the claim is that string theory involves quantum gravity. So this in certain regime, namely precisely in the regime where the coupling is strong, string theory can be approximated by classical gravity, meaning that we just need to solve Einstein's equations linearized near the background, which is the entity space. This is, should be equivalent to four-dimensional theory, which is just, which is the gauge theory, but with this extra extra symmetries that are related to supersymmetry. So this equivalence is still a conjecture. However, there is a number of quantitative tests of this conjecture which, well, it's by many physicists, they are this is regarded as an empirical proof. Of course, it's not a mathematical proof. It's, in a sense, theoretical experiment. We can compute certain quantity explicitly, and then on both sides, and then check that it is the same, gives the same results. So I'll try to explain how this works for some very specific quantities, and in the course of these calculations, the matrix models will naturally appear. So the objects that I'll concentrate about on are Wilson loops, which are certain quantities in gauge theory. Important point here is that a Wilson loop maps a contour in space-time to real numbers. So it depends on the contour, and for any contour, it produces some statistical average that, is the Wilson loop expectation way. So the gauge theory that is involved in the Moldacena conjecture is a modification of the Yang-Mills theory by adding some extra fields, namely scalar, and one should also add fermions, that make this theory supersymmetric. So there are some extra symmetries which are important for the calculations that I'll be talking about to be valid. Okay, so returning to Wilson loops, the dictionary of the holographic duality claims that at strong coupling, their expectation values have a nice geometric description. Namely, they satisfy the minimal area law. So if we are given a contour in space-time, so remember that space-time is a boundary of a five-dimensional space in which strings can propagate, we need to draw a two-dimensional surface that extends in the bulk of this space and find the minimal area. So find the minimal surface that has the smallest possible area with a given boundary, and then the expectation value of strong coupling will be exponential in this area with known coefficients. So let's see how it works for the simplest case where the contour that we take is a circle. So if we have a circle on the boundary, so in the coordinates x in the entity zeta metric, then the minimal surface with the boundary of this circle is actually also very simple. It's a hemisphere, so it's given by this equation. So r is the radius of the circle. X is just a coordinate in this boundary plane. So what we need to do is we need to compute the area of this minimal surface in the given metric. And when we substitute this into the if we simply compute the area, integrate the area element of the surface, we find that the result is infinite. And the claim is that what one should do is one should regularize this by computing the area by cutting off the slice of anti-de Sitter space that is near the boundary, and then subtracting the divergence. So what is important is the regularized area, which turns out to be negative. So for the circle, we have a concrete prediction that its expectation value should be proportional to e to the square root of the coupling constant. Now, what does it have to do with matrix models? Well, the claim is that if you start from Yang-Mills theory, and even if you don't know anything about the ADS-CFT correspondence of the holographic duality, the exact answer for the circle Wilson loop is given by the expectation value of the matrix model. So this is a very non-trivial statement. So originally, we have dynamical variables that we have are fields in space-time, and so we need to average over fluctuations of all these fields independently, well, not quite independently, but also in each space-time point they can fluctuate. Whereas the claim is that for the circle, only fluctuations, overall fluctuations that are constant in space-time matter. So this is a consequence of supersymmetry. I'm not in a position to explain this, because of the lack of time. But here is the result, that the expectation value of the circle Wilson loop, maps to the expectation value of trace of exponent in the Gaussian matrix model. And we know how to solve the Gaussian matrix model. We just start with the Victor distribution. So if you have, so the answer is given by the integral of the exponent with the weight given by the square root formula of the Victor distribution. So this integral can be easily done, and it produces the modified Bessel function. Which is the exact non-perturbative result that describes the expectation value of the circle Wilson loop at any value of the gauge coupling. So I would like to stress that such results are really very rare in field theory. So usually we are not able to calculate exactly, and so here, because of a lot of symmetries, it was possible to produce such a simple and exact expression. And indeed, it interpolates between Taylor expansion at weak coupling. These first two terms can be, this is what one would get by applying usual fading diagrams to the circle Wilson loop. But when we go to the opposite regime of strong coupling, when normally we don't have any tools to calculate the error in field theory, so here we have an exact expression. We just use the asymptotics of the Bessel function. What we find is the same expression that were predicted by this geometric picture of string theory. So we get the same exponential, and the exponential factor also matches. So this is one of the checks of the holographic duality that one can make by just computing explicitly in field theory and then comparing to a simple geometric picture predicted at strong coupling by ADS-CFT correspondence. This calculation has relatively straightforward generalization to the cases where we take Wilson loop in higher representations of the gauge group. So normally we would take a trace of the exponential to compute the Wilson loop in the defining representation of SVM, but one can take a trace character in any reducible representation. Well, just for the sake of simplicity, let me consider purely symmetric and or antisymmetric representations of rank K, and then there is a regime. So one should take the large n limit. It turns out that a non-trivial regime where we can explore here is when we at the same time send the rank to infinity while keeping the ratio of K to n fixed. So there is an interesting way to reformulate this problem, namely if we introduce a generating function of characters, of symmetric and antisymmetric characters. They have a nice interpretation as partition function of free bosons of fermions occupying energy levels at some chemical potential. So this variable mu is just a counting parameter of various representations. Then if we consider, so if we diagonalize the matrix of which we are taking the trace, then the eigenvalues, well, in the original work of Wigner and Dyson, these were interpreted as energy levels, and so if we interpret them as energy levels here, this would be a partition function of non-interacting particles subject to a chemical potential mu, and whose energy levels form a set AI. And then, as a result, the formulas for the expectation values of the Wilson loop take a form that is, well, very familiar from statistical mechanics. So the result exponentiates, and the exponent is the free energy of Bozo-Fermi gas, depending on whether we have taken symmetric or anti-symmetric representations. Where nu plays the role of chemical potential and F of the particle density. And so nu is actually an auxiliary variable that should be excluded by minimizing the free energy with respect to it. And this gives the, this is a well-known formula that transforms grand canonical partition function to the canonical one. And so this would be the answer, where rho is the density of energy levels. So this would be an answer for any system of particles whose energy level density is given by rho. So in our case, the energy density is given by the Wigner distribution, so we just need to substitute the square root Wigner formula for rho and calculate this would produce the answer. So the interpretation here is that if you consider Wilson loop in the fundamental representation, then this maps to Wigner distribution of eigenvalues of our random matrix. The problem is equivalent to considering the statistics of energy levels of the system in which the Hamiltonian is a Gaussian random variable. Now, if we consider higher representations, this would be the same, but when we consider many-body problem in the same random Hamiltonian, such that the number of particles maps to the rank of representation, the matrix size plays the role of the volume, and so the ratio is just particle density, and this auxiliary variable mu is the chemical potential. Well, the result here is pretty simple. We just need to compute some integrals. So let me give you the final answer. And the most interesting is the regime where the coupling constant is big, because then we can compare it to string theory. So here is the result for the symmetric representations. When we consider Wilson loops in higher representations in string theory, what happens is that the string actually develops, it puffs into something that has bigger dimension. So in string theory, there are objects called D-branes, so if you consider Wilson loop and symmetric representations, then what happens is that depending on the size of the representation, the Wilson loop will become, so this two-dimensional surface that describes the Wilson loop will actually become four-dimensional. So at each point here would expand into small two-dimensional sphere. Again, we will need to minimize the four-dimensional volume of the resulting figure. So if one does this, in the symmetric one finds exactly the same result, which is another check of ADS-CFT duality. So for anti-symmetric representations, the picture is more or less the same. But here the string extends into a six-dimensional volume of D5 brane, and also it expands not into the Sitter partial space, but on the 5 sphere. So the dual geometry is direct product of ADS5 and S5. And so the six-dimensional volume would have a component, two-dimensional component into the Sitter space, and then it would subtend a four-dimensional subspace in five-dimensional sphere. So in the most symmetric configuration that minimizes the area, it would sit at some particular, this would be a four-dimensional sphere sitting at some angle theta within S5. Since the angle in S5 only changes from 0 to pi, there will be certain, so the variable that was characterizing the representation in which we considered the original object we are studying, namely the Wilson loop, will also have a limited range, and this is not accidental, because for antisymmetric representation of SUN group, the rank can go only from 1 to n, and so the ratio of k to n goes from 0 to 1, and this is, well, consistent with the fact that theta goes from 0 to pi. So but now this has a clear geometrical meaning, because this sphere first starts to expand, then it reaches the maximal size, and then it contracts again. And in fact, there is a symmetry of theta going to pi minus theta, and that's actually complex conjugation symmetry for Cartesian representations. All right, so all these results, they just follow from this simple Gaussian ensemble that we haven't used anything more than Wigner's semicircular law. But if we start to look at more complicated gauge theories, then it turns out that one can extend these results to a bigger class of models at the expense of producing more complicated matrix integrals. So in particular, there is so it actually works for any Yang-Mills theory with n equals 2 symmetry, n equals 2 supersymmetry, but so as a particular example, when we consider a deformation of n equals 4 theory that is obtained by giving masses to some of the fields. So what happens then is that instead of the Gaussian matrix model, we get a model where the weight is modified. So you see that so in this integral, in the eigenvalue, so in the eigenvalue representation, the weight is requires some extra factors that are given in terms of some special function. These extra factors cancel if we set m to 0, and this is precisely the limit at which we recover the original full theory. So the deformation parameter here that is related to the mass of the particles, some particles in the theory, this is the parameter m. But at large n, this model can be analyzed by the same methods. So the integral is of the Sevel-Floyd type. So in the large n limit, we just need to solve for the equilibrium configuration of eigenvalues that minimize the weight in, actually maximize the weight in the integral. So surprisingly, this gives a result that is produces a rather rich phase diagram. So there are quantum phase transitions that happen as we vary the coupling from weak to very strong. And technically, what one has to do is to solve this type of integral equation with two normalization conditions. So this equation depends on two variables, m and mu. Mu is just the boundary of the interval in which the eigenvalues are concentrated. And this equation is homogeneous, so we need to fix normalization of the density to 1. So this is one condition, and the other condition relates mu to lambda. So mu is actually not an independent variable, so the input variables are m and lambda. So lambda is the coupling constant. It controls the strengths of interactions in the gauge theory. M is the mass of scale of the particles. And then, given these two variables, we need to solve this system of equations. So when lambda is not too big, these equations can be solved exactly using, in terms of elliptic integrals. And so the trick here is to recognize that, so first of all, one has to analytically continue to complex masses, and then introduce this function that's usually called resolvent. And one can recognize that the integral equation written before is equivalent to the condition that the resolvent is real along this contour in the complex plane. It's not very immediately clear, but with a simple two-line calculation, one can show that this is true. Moreover, so since this function is real on that contour, its imaginary part has a definite sign inside, so in this quadrant of the complex plane, and so it maps this quadrant into upper half plane. Okay, so this line maps to the real line, and the interior maps to the upper half plane because the imaginary part is well, constant sign. Well, it is well-known fact that a map that from such figure on the upper half plane is unique. It's a Schwarz-Christoffel map, and the inverse of it can be written in terms of elliptic integrals, and so this gives the inverse function. So it gives a function that's inverse to g of z. So it expresses z as a function of g. So if one scrutinizes this equation, it turns out that it only holds up to a certain value of the coupling constant and cannot be continued beyond. And so this is the point where the first phase transition happens. So beyond that point, the density develops singularities inside the integration domain, and I don't know, we were unable to solve this equation analytically, although numerically we have pretty much we have a good control over what goes on. But then an interesting question is what happens at extremely large coupling, where lambda goes to infinity. And so the answer is actually rather interesting. So the density becomes more and more complicated. It develops more and more singularities as lambda grows. But then the average density is again the Wigner-Seeing circle. So what we get is again the Wigner distribution, and we can play the same game with comparing to string theory, and it works perfectly. But the string theory seems to be sensitive only to this average distribution, and a question that we still were unable to answer is how this complicated Rig structure appears in string theory, that we don't know. So let me stop here. Thank you.
Are there any questions?
I was wondering if you went to the recent meeting in Sweden with Stephen Hawking and the Hooks.
Just hold on for there's a microphone.
I saw in the news that recently there was a meeting in Sweden.
It's working now? Right. There was a recent meeting in Sweden I saw in the news with Stephen Hawking and De Hooft were there. Since you're from Norway, did you attend this? Or it was about, they meant that Hawking actually supported the holographic principle with respect to the black holes, his theory of black holes.
Unfortunately, I missed that event, although, yes, as you mentioned, I'm from Sweden, and I guess from this distance, Norway and Sweden is. So, indeed, there was a conference where apparently there were a lot of progress made towards understanding understanding the black hole information paradox, in particular using holographic principle. So this has not been published yet. There was a preprint by Hawking himself. It's 1.5 pages long. And I mean, it's very too concise to comment.
There are, of course, different ensembles of random matrices that we like to study. It wasn't clear in your talk what role the different ensembles were playing in your... because you seem to more use this as a tool to actually compute things explicitly, but...
That's a good question. So if you was to start with, so that in some sense that's in our hands. So we can choose to work with the orthogonal group that would connect to orthogonal ensemble, symplectic group that would connect to symplectic ensemble. So the answers are sort of similar. So the most interesting gauge theories that are closest to the theory of strong interactions, which is SU3 gauge theory, and this is what we want really to understand, are obviously they might be unitary ensembles. That's why I've chosen to speak about that. But one can consider other types of ensembles. The results are actually very, very similar.
Well, yes, I was just wondering in terms of mathematical tools and techniques. I mean, you got up on the slide there that you're now using matrix models of a new type. And so the question is, do all of the assumptions, tools and techniques that were used in the old type of matrix model carry over to what you're doing, or do you need to invent something new in terms of random matrix theory to be able to deal with your new models?
We certainly need some new tools. So up to this point, yeah. So the Lagrangian matrix models. So this matrix model boils down to an integral equation, which is standard thing in matrix models. But this type of integral equation is, as far as I can tell, new. I couldn't find any literature on it. And by ourselves, we were able to solve it in full generality. So,
I think that's it. Due to time, let's thank the speaker once more.